Welcome to the fourth episode of the Query Writing Best Practice. In the beginning, I will introduce myself a little bit. I'm Xinyu Chen. I'm the Director of Customer Solutions. I have been with the company for about 6 years. So during these 6 years, I have built a solution for a lot of major customers. They are from all kinds of different industries. And also, I worked in the language team for about 2 years. So I personally implemented many GSQL features, so I know the language inside out. So I want to share my experience. What's the best way to write a query to have the best performance and also utilize the system resource wisely. Okay, so so this will be today's agenda. So in previous episode, we talk about what to think about when we write a query, what is the best way to manage the memory, what's the best way to design a good traversal pattern, right? And in today's episode, we are going to talk about how to parallelize your query to achieve the best performance, as well as how to do pre-processing in order to support your analytic. So in order to talk about the parallelization of TigerGraph, we have to talk about its MPP mechanism. MPP is for massive parallel processing. But in order to understand MPP, we have to talk about the distributed native graph storage first. We have to understand the storage in order to understand the MPP mechanism. But in order to understand the storage, we have to know how's the query execution flow look like. Then we know what's the function of each component storage. Okay, so I will start with the execution flow and then talk about the storage and then dive into the MPP mechanism. And then I will show you what's the best way to write the query to make it like a fully utilize the resource, to make it really run in parallel. And at the end, I will talk about what are the good use cases that we do pre-processing, and I'll give you a query example on how to do pre-processing. I put them into one episode because we don't have much content on pre-processing, but that is also very important. Okay, so query execution flow. So I actually talked to these slides in previous episode before. I will just review it again. So this is the execution flow of GSQL query. So here is the request sent by the user, and the request will be sent to our web server engines, and the engines will send it to the REST VP. REST VP is you can consider it as like a load balancer in our system. So when it receives the request, it does two things. Because the request having all kinds of parameters saying, okay, I want to run this query and here are the parameters. And in this parameter, some of them are like vertex IDs, right? I want to start from a certain vertex. Then, okay, so then, but with the external format vertex ID, like string ID, right? We cannot find it from the graph. We don't know where to start from because it's an external format. That means we need to translate the external ID format into internal ID so that they can be found from the graph storage, right? So that we'll need help from GSE in order to translate the external ID into internal format. And the internal ID will be sent to GPE. That is our graph process engine, okay? And in the meanwhile, REST VP also will send all the query names and the parameters to the GPE. And at this point, GPE got everything it needs in order to process the query, including the query name, the parameters, and also the translated internal format of the vertex ID so that it knows where to start from. So once it got everything, then he would just do the MPP process, massive parallel processing, and do graph traversal, compose the result, and then once the result is composed, it's still in internal format, right? Because GPE doesn't have any external ID information. Then GPE would just send the ID in the internal format needs to be translated to GSE, and GSE will translate it into an external format, right? Those are the IDs so that we can read the username, email address. so on and so forth, right? And also GP will send the JSON response in the internal format to the REST API, and then REST API will just combine the two, right? Translate all the internal format in the JSON response and send a finalized result to engines, and the engines send this whoever send the request. So this is the execution flow. So from this execution flow, we can see that this GSE part and GPE part, they have the graph storage, right? GSE carries the ID service. ID service is a bidirectional external ID to internal ID mapping. When we receive the request, we need to translate the external ID to internal format so that GPE can find the location of the vertex. When we send the result, we need to translate it back into external format so that the users can read it, right? So this part called IDS, called ID service, is a bidirectional mapping of external ID and internal ID mapping. And also we have another two part that is vertex partitions and edge partitions. Pardon my typo, this should be edge partitions, okay? So vertex partitions store all the vertex info, including the vertex internal ID and all the vertex attributes. And the edge partitions, it stores the source vertex internal ID and the target vertex ID because an edge has two ends, right? The source vertex end and target vertex end. So it requires to store two IDs for each map, for each edge. And also we will store all the edge attribute in the edge partitions. So we have, you can think we have three types of storage: ID service, vertex partitions, and edge partitions. So I really have to correct myself here. This should be edge. Okay. Okay, and so we know that we have this three type of data stored in this in the graph as those are our graph storage, and so there are a few things that we need to know as well. So each component of the data of different components are split into segments. Okay, so it's not just big chunk of data; they are split into small pieces, small chunks, so that we can run parallel processing on them. And the next is that the segments are stored distributed across the cluster. So we cut the big chunk of data into small pieces, and then we store the small pieces across the cluster distributedly. Like in this case, each server will store 6 segments, right? And they are all different segments on different server. And also, the segment of different components with the same ID stores the data for the same set of vertex under the same vertex type. So in this case, this segment 13, they must contain the set of vertex under the same type. And they also contain the same set of vertex. Okay, so by giving an internal vertex ID, we can predict, not predict, we can calculate the location of that vertex. We can say, oh, given this internal ID, we know which segment it belongs to. Therefore, for this vertex, if we want to look for its vertex attribute, you can locate the vertex partition 8 from here, vertex segment 8, number 8 here. If you want to get all the edges, then you just go to the edge partition segment 8 to find all the edges of this vertex. If you want to find its external ID, you go to the IDS segment number 8. Okay, so this is how we store this native graph distributedly. Okay, so based on this type of storage, how do we run the MPP on it? Okay, so first thing, say if we got a server with a CPU cores, and these are all the segments stored on this server. The red is IDS, green is vertex, blue is edges. So if you run a query, say, okay, I want to start from all the users, and then I run the post accum clause, define some logic there. So in this case, if you want to start from all the user vertexes, then the system can figure out, oh, okay, so segment 2, 4, 5, 6, 8, they are user partitions. Though I want to run this post accum logic against all these segments. Okay, and then next step, the CPU will assign the thread to every each segments that needs to be processed. And then that means all these calculations for each segment, they are in parallel. Okay, so since they are in parallel, then so if for each thread, once the task for this segment is done, it will just move to the next one that is not processed yet. So you always keep the threads busy until all the tasks of different of all the segments are done. Okay, so this is an example how we process the logic defined in post-accum in parallel. Also, in the same way, if it is a vertex-induced accum or where clause, they are in parallel too. Or is a post-accum or having clause, they are all run on the vertex partitions or segments in parallel. Okay, and here is similarly, this is the example how we process the logic defined in where clause, accum clause in parallel, right? All we know that for this edge-induced accum clause, they run on edges. So in order to run it on edges, the tasks will be performed on the edge segments. Those are the in blue color, right? Then again, we say, okay, for all the users, we want to run this logic for their edges. That means these segments will be selected, will be processed, right? And then in the same way, CPU, the system will have the CPU assign one thread for each segment, and all the segments are processed in parallel to execute the logic defined in the accum clause. Okay, and that's how we process edges. And this is how we process the task distributedly. Because sometimes we store the data distributed like on two servers. You can see now we have two servers. Each server stores almost the equal amount of segments, but they are different segments. The first server stores 1 to 10, the other stores 11 to 20, right? And then again, if you want to run the processing for the user vertex, then first step is also find the segments first, and then assign the thread. And this process can be also done distributedly, not on one server. All the servers can do the calculation together. Okay, so coming to the distributed, like running a query distributedly, we actually have two execution mode. Those are that is single server mode and distributed mode. So when you define a query, by default, it runs in single server mode. Okay, so if you have stored the data distributedly, and each server stores about 1/3 of the data, right? And now say server 2 received the request and start to run the server in single server mode. Since one server doesn't have all the information, it only stores part of the graph. That means during your graph traversal, whenever you want to use some data that is not in this server, we have to fetch it from other server. That requires some data shuffling, that we need to get the missing part from other nodes in order to complete the graph traversal. So that is the single server mode. However, there is one thing we need to alert about is in single server mode, if you have a very large graph, you store it distributedly, we should be careful. We should be careful when we start from all the vertices. Because if you run that type of query, starting from all vertices in single server mode, that means we need to collect all the partitions or segments from all the other servers to one node. And that will blow up the memory, right? And also, similarly, we have distributed mode. As I mentioned, the default mode is single server mode. So to enable the distributed mode, that is, when you create your query, you just need to use the keyword distributed query, and then followed by the query name. And anything else, right? Just use this distributed keyword in order to enable the distributed mode. So in distributed mode, it's obvious, right? Based on, according to its name, we know that all the servers does the graph analytic graph traversal together in parallel, also distributedly. They only process the part that is stored on that server. So server 1, 2, and 3, altogether, they will handle the distributed query processing. Okay, and they don't only take care of the graph that is stored on their storage. So this time, the communication between the servers will be the accumulators, the global accumulators, local accumulators, target attributes, as well as the activated vertex set. Right? If I want to activate the vertex on your server, then I have to, like say, I need to activate the vertex on server 2, then I have to let server 2 know, hey, I want to activate one vertex from you. Yeah, that's how distributed mode works. Then now you may have a question, okay, when should I use a single node, single server mode, and when should we use distributed mode? That's a very good question. So by comparing the two, usually the rule of thumb is like if your query only start from a single vertex or a small number of vertex, and it only traverse the modest number of vertex and edges, it's a tiny query. It runs edges like below, say, 1 million. It's not very big. Then usually a single server mode will give you better performance. However, if you, on the contrary, if you start from all vertices or very large numbers and you traverse very huge amount of vertex and edges, then it's a good idea to run in distributed mode. Okay, and also if you don't use the global accumulator very intensely, then the distributed mode is also a very good choice. Okay. Okay, so how do we utilize the MPP mechanism? How do we write queries that can actually run more parallel, right? So a few things. Sometimes a user may write a query like this, right? We can collect a data structure, we populate a data structure like for this query, right? We define a set in the beginning, and then we populate it with a lot of vertices. And then we go over the set, and then we say, okay, for every vertex in the set, I want to do logic such and such, right? Because we know that when I explain how accum clause and post-accum clause that performs the operations, the calculations in parallel, right? That's where the parallelization kicks in. We'll run GSQL queries. So that means everything outside this accum clause and the post-accum clause, they are in sequential. For example, this for each statement, right? So all the logics in the defined inside this for each loop, they are done in sequential, right? That means I have to process one vertex and another. Then if you have like millions of vertex in the set, then this select statement will be executed a million times. That takes a lot of time, right? So in order to improve this problem, we can actually do it in a query calling query way, right? So we can migrate the logic that we need to run in the for each loop to a subquery, right? We define the subquery here. We are running the same logic, and then we call the subquery from your accum clause because we know accum clause are run in parallel. Remember how the CPU processes the segments? That's how they run the subquery. Okay, so in this way, even you want to call this subquery a million times, however, they are in parallel, the performance will be a lot better. Okay, that's one thing. Another thing is sometimes we can write in the same way. If you want to output the result into a file, right? We take the file as parameter and we populate the data structure, and now we want to print the content of data structure into a file. However, the size of the data structure can be very, very big. if it has millions of elements in the data structure, then we have to run this print statement a million times. So better way of doing this, because we are getting the attribute from vertex anyways, right? We can move the print statement into the accum clause. This way, the file writing becomes parallel, right? And it will be a lot faster. And even better, and not necessarily better, but alternatively, another way of doing this is we can even do it from the subquery, right? Because we can pass the file parameter into as a parameter to the subquery, and from the subquery we can do all kinds of printing as well. Okay, this works if especially you have some more complex logic in your subquery and you want to print something out from there. Then this will help you to improve the load output file output performance effectively. Okay, so that's all I want to talk about for parallelization. And the next, I will talk about preprocessing. I will give you a full examples like what are the good use cases of preprocessing, and in the end, I will give you a query example on how to do preprocessing. Okay, so the first thing we can do is we can build a derived edge. That the derived edge doesn't exist in your input data. It's something that we calculated by running graph analytic, and then we insert them as an edge, and then it becomes a part of your graph, right? We can update the graph schema to include this new relationship, and then with this new relationship populated, it will support your future analytic, make it a lot faster. So for example, say we have enterprise graph, right? The company has their parent company, and the parent company has the parent company or parent company. And then if we go all the way up, we have alternate parent company. Okay, so if you have a query frequently search for the info of ultimate parent company, then sometimes we can consider, okay, we have to traverse all the way up every time. Then why don't we just create an edge for the ultimate company edge, right? Then you want to follow the steps. We want to create a new edge type called has ultimate parent company in your schema. You can change the schema from a Graph Studio, or you can run a schema change job. If you search for schema change job, you can find it from the document. And then once this new edge is created, we can run the preprocessing query to create this type of edge, right? We traverse from each company and traverse all the way up, and then we can get the edge connected, or we can push down the ultimate parent company ID to each company. Then we know, then we can connect to the edge, right? And then in the future query, you can just utilize this edge. Then you have a lot better performance. You don't have to go all the way up every time now, right? Okay, another example is not only the edges, we can also store this info in your attribute. For example, like in some of the query, like it frequently traverses the companies and want to use the value of number of subsidiaries. You can collect all the traverse multi-level to collect all the number of subsidiaries, right? That's slow. However, you can also add this Boolean type or integer type attribute to the schema first, and then you can run preprocessing query to populate this attribute. And then you have the numbers already stored on the graph, right? And then you can just use it whenever it is needed. You don't have to do actual traversal in order to access the attribute. And then here are two more examples. I think I have mentioned this in our schema schema design best practice. So for example, doctor has claims from a patient, and patient also have other claims of that with other doctors. So if a patient has consecutive claims, that means the doctor may refer to another doctor, right? So in this case, if we want to say, we want to run the PageRank algorithm to find the most influential doctor in the network, then if we directly apply the algorithm in this graph, it will be too much noise, right? The doctors are very far away with many patient and claims in between. Then the page rank score may not be accurate because there are too many noise in between. And then if we can pre-process the graph, connect the match between the doctors that had a referral relationship, and then by utilizing this edge, we have built a network like this, right? Then after that, if we run the PageRank algorithm, we get a more accurate PageRank score, right? Because all the edges are actual referral relationship. Then it will make our job a lot easier to find the most influential doctor in the network. So this can also, so not only the performance, they can also sometimes improve your accuracy of your result by doing some pre-processing. Also, the last example is given the graph like this, we have product type and we have products under product type, and the products have attribute, and the attribute can shared by many products, and each product also belongs to a product type, right? So think about this. How can we run, say, cosine similarity or any similarity algorithm between the product types, right? If we think about it, now the product types, they are very far away. So the difficulty of writing this similarity algorithm is super high. It's really, yeah, it's really hard. I tried that and I had a hard time writing that. And then if you can actually do a pre-processing and connect your product type and all the attributes that belongs to the product under that product type, and you can connect the edge like this with a pre-processing query, then the job becomes a lot easier. You can just get the cosine similarity number query from our GitHub and run it. It's very straightforward. You don't have to worry about all the other logics. So that makes the query writing job a lot easier sometimes by doing a pre-processing. However, before you do pre-processing, we know that we can get all these benefits by doing pre-processing. However, there are a few things for you to think about before you do it. For example, we have to evaluate how many edges might be created if you want to do pre-processing. Does it create millions of edges? That might be okay. Like for example, each product type may have very limited amount of attributes. This one is fine, it's okay, right? However, if after evaluation, if we do pre-processing, it insert 100 billion edges, that might not be a good choice, right? We don't even have enough memory to store the 100 billion edges. So that's the one thing that is really important to consider when we do pre-processing. That is because pre-processing usually is like we trade the memory for better performance, for easier query writings, right? However, we need to evaluate how much memory do we have in order to make this trade, okay? And here, last, this is a query example of this use case, okay? How this shows you how we can insert a new edge between the product type and the attribute by running these two queries. This is the main query. From the main query, the subquery is called, okay? And the subquery is defined right here. It takes the product type vertex as an input, and then start from this product type, traverse to all the products. And also, we want to count the number, how many products are under that, had that attribute, right? And then from the attribute vertex, we start from product, get to the attribute, and then from the attribute vertex, we want to insert an edge, right? Insert an edge between the product type and the T. What is T? T is the attribute, right? Because we are starting from product. And then between the attribute and the product type, and store the count as a weight on the edge. So after running this main query, it will execute the logic in the subquery for each product type. This way, the edges between product type and attribute will be defined. And then it will become 100 times easier when we run this analytic, right? We just get an algorithm from here, change a few edge types, and you can get your analytic result really easily. Okay, and that's all the content for today's webinar. Let me check. Let me take a look at the Q&A. Okay. How do we handle interactions among segments in particular? Right. So this is a very good question. The question is, how do we handle the interactions between segments? So as I mentioned, when we run the single node, single server mode, right, we need to fetch the missing information from other servers. And also, we also know that in the like edge storage, right, we don't have the info for the, like I say, if we want to get a target attribute value, right, we need to get it from the vertex segment. However, for example, if from this segment 6, we are trying to, there is a from vertex 1, 2, 3, and the target or the 4, 5, 6, and then now say, oh, I want to also use, because from a Q class you can use target attribute, right? And the 4, 5, 6 may be on another server. I'll use this example, okay? So 4, 5, 6 may be here. In this case, we need to transfer this guy over in order to finish the logic in the Q class. So that means you should expect some shuffling when we handle those segments. And we should also, for the best performance, we should be careful when we are using target attribute, because using target attribute or target accumulator may increase your shuffling amount. Okay, let me see. Yeah, now if anyone has any question, you can just post it in the Q&A. Okay.
There's one in chat, but I'm not sure if you can see that.
Let me see. Would you please last please a code inside again slower? Okay, sure, gladly. So I will explain this slower this time. Okay, so you can see that we have two queries defined here. One query is the main query. Okay, from the main query to start from all the product type, because the problem I'm trying to solve is to answer this question, right? We want to calculate the similarity between product type. And now I want to connect the edge between product type and the attribute. So now I have a main query start from all the product type. And for each vertex in this vertex set, I call this subquery, okay? And the subquery is defined right here. It takes a product type as input, and I create a vertex set variable starting from this product type, right? This guy goes here. And then start from this product type, I use product type to product edge to traverse to product. And along the way, I will, oh, actually this logic should be here, my bad. Okay, so let's assume we have moved it here, okay? And then start from the product, we want to traverse to attribute, right? And then on each attribute, we insert an edge between the input product and the attribute on the target, right? So let me draw it maybe more clear. Like for one product type, we get to all the products here, right? And for each product, we traverse to an attribute, and then also I maintain a count, right? Then this have count 2, this guy have count 3. And for each attribute here, we want to insert a new edge between the product type and the attribute, having the weight stored on the edge. That is what this query does. Okay, hope this helps. I think we just get more questions. What are the evaluation metrics when adding an inferred edge? Evaluation, could you elaborate what do you mean by evaluation? Oh, okay, I think I mentioned that. Like how do we what to think about when we add in for the edge, right? Like I mentioned, you want to think about how long, like first, how many edges will be inserted. Make sure that it is not too gigantic, like will blow up your memory, right? And another thing is you also want to evaluate like how long it may take in order to insert those inferred edges. Sometimes, like if you want to run the pre-processing for like 1 billion vertices, that might be too much subquery to call. Then you have to think about other techniques in order to improve the performance. And I'll see next. If you do pre-processing, how do you handle changes in the data? Well, the data, I don't know what do you mean by data here, right? So usually when we run queries in this graph database, we already ingest the data and now they are in the form of graph. So once the pre-processing is done, we update the graph, right? We have nothing to do with the data ingested anymore. We just manipulate whatever in the graph database. Let me go to the next. How single mode query and distributed query are related to a single node HA installation? Can we single mode query? Okay, this is a very good question. So if we have a HA installation, right? And say if we have 3 node HA, if we run distributed mode query, hopefully the distributed mode query will be run on just 1 node. Okay, the behavior of the distributed mode query will be very similar to the single mode query. Because we are like in active mode, all the 3 servers will process query together, right? However, in the 3 node HA case, then one query only goes to 1 server. Because we don't store the graph distributed, right? And distributed query is a single query distribution mode, single mode installation. Yes, we can do vice versa. If we run a single query in distributed cluster, then it will be like this. Like I mentioned, right? It will fetch the missing partitions. And we can also run distributed mode in single server mode, but the behavior is like if we run distributed query in a single node, the behavior is very similar. Okay. Let me see. Okay, I think that's all the queries. So Emily, do you want to wrap up?
Yeah, I think that you've answered all the, wait, we have one more, I think, sorry.
Nope.
Let's see. Oh no, it's just saying, he's just saying thank you.
Oh, okay.
So I think, yeah, I think we can wrap it up. And wait, we have one more question.
Okay. One more question. Anything can improve the performance of order by clause? Order by clause, itself is like an operation with a higher complexity, right? Because we need to order all the vertices in the vertex set, and inevitably the complexity will be n log n, right? And it requires to use some heavyweight data structures to maintain the order. We need to populate the vertices into that structure, and then we can guarantee the order. So if you have performance issue over the order by clause, I think one thing you can do to mitigate that is that you can populate the vertex into a heap. That is more lightweighted than using order by. That's one thing you can try to do. Okay. Yeah. I think that's all.
That's it. Yeah.
Yeah. Okay.
Okay, do you want to go to the next slide and show the resources if they have any more questions? Okay, great. Well, so if you have, you have the links to this, but we have a great community forum that you can join if you have other questions, in addition to, contacting support if you're a customer. And then every Thursday at 11, we have our office hours where you can get one-on-one support via, online support with one of our engineers. So that's, again, every Thursday at 11 a.m. Pacific time. And then if you go to the next slide, Shinyu, the webinars, let's see. Okay, we will email you a link as well to our upcoming webinars. And then every Friday, we have an online demo. If you actually want to see a demo of the product, full demo of the product, we do that every Friday. And then we have Test Drive, which is our online test drive demo, in addition to the cloud, which is free, developer edition is free. Everything is free for you to try. In addition, we will send links to all of these, including our Graph Gurus master scripts. So I think we're going to go ahead and end today. Thank you so much, Shinyu, for presenting, and we'll be in touch with everyone via email.
Okay, thanks everyone for coming. Bye.
Bye, thank you.